So let me introduce our next speaker is Yuriy Drozd from Institute of Mathematics of National Academy of Science, and also now he is in Harvard, yes, as I know. And the title of his talk is Backström curves. Yuriy Anatolyevich, please.
Thank you. This is a survey of some recent investigations in algebraic geometry, including non-commutative algebraic geometry. The main results of this talk are in arXiv, and right now it is also in Pacific Journal. Okay, I'll start with a simple example. This is a usual nodal curve, nodal cubic. In affine coordinates, it's given by this one, but it looks like this. Okay. Vector bundles over this cubic were classified by Groyle and myself. And we noticed that this classification is very much alike to the classification of the representation of the following algebra. As usually it is done now, I present an algebra quiver, that means oriented graph, with relations. So we consider the paths of the quiver, and we put the relations B1, A1, and B2, A2, R0. This is a rather simple, yeah. Certainly, and the vector bundles over this nodal cubic and representations of this algebra are very much alike from the point of view of classification. Okay. Certainly, we knew that the analogous relation exists between the projective line and the Kronecker algebra, the path algebra of this, the simplest quiver. But it was explained by Beilinson that derived categories are equivalent. But this explanation doesn't work in our case by the very simple reason, namely the global dimension of this algebra is 2, and global dimension of sheaf of regular functions on X is infinity. So derived categories cannot be equivalent. Okay. Then Igor Burban and I solved this problem by introducing a resolution, a new resolution of X. You see, the usual resolution which for the curve normalization doesn't work on this case because the vector bundles over X and over X tilde are not very much alike. Over X, they are much more complicated. We propose another resolution. You see, by this time, there were known several categorical resolutions of singular curves, but all of them had one important important gap. They could not be, they were not derived categories of some curve, of some algebra, or something like this. The novelty of our construction was that we realized it as coherent sheaves over a curve, but over a non-commutative curve. Namely, what we did, we considered the following sheaf, namely endomorphisms of the following. We took OX and plus OX tilde. X tilde is just a normalization. But in our case, it is just projective line. You know this normalization. You take projective line, you take a map which maps 2 points to this one. Then this one maps here. Yeah. This one maps here. And the last one, this one, maps here. Yeah. This is a well-known resolution of the. Let it be A. Then we consider the non-commutative curve. It consists of our curve X and the sheaf A on X. This is a non-commutative curve. And we consider coherent sheaves where A, yeah, and there is so-called recurrent, which means the following diagram. We have natural projection F. It has both left and right adjoint. This is left adjoint. This is right adjoint. And moreover, they have a very nice property, namely both of them in some sense inverse of F, namely F star and F this one are equivalent to the identity functor of cox. Then certainly we have here a kernel F. It is embedded here. And this embedding also have right and left and right. So we have this one. Moreover, in our case, kernel F is equivalent to the modules of this one. Well, K is the basic field. So coherent sheaves over X and over A are almost the same. The difference is very small. But A has a lot of advantages. First of all, it has finite global dimension. Its global dimension equals 2. So it is in some sense regular. Yeah. That is why it can be called a resolution. So this one is a categorical resolution of this one. Yeah. Moreover, the same recurrent is also for derived categories. Categories of coherent A and coherent X. And moreover, we can calculate the so-called derived dimension of A in the sense of Rouquier equals to, it is not evident, but one can prove that the derived dimension to the dimension of the derived category as of triangular category in the sense of Rouquier is 2. And since we have this recallment, this one and this one, implies that derived dimension of X is also 2. It is a rather new fact. Moreover, analogous facts hold also for any curve with nodal singularities. Nodal means for any singular point, there are 2 branches which 2 transversal branches. So locally it looks like this. 1 branch and another one. This is so if we have something like this, then the same construction works. Moreover, what is new? The same works always when the endomorphism ring of the maximal ideal for any point F is O X tilde, where X tilde is the normalization. In some sense, locally everything is like this. We have, this one is of course discrete valuation ring or product of discrete valuation. So we have this O X tilde X. And no, that's not all. And mx equals mx equals is the same as radical. We have X tilde S, then we have its radical. Yeah, and O XX is in between, something like this. Example, we take a union of X's, let's say in affine space. If n equals 3, it looks like so all singularities, for instance, like this. The same is for any dimension. That was in some sense a starting point, but we can also consider non-commutative analogs. which I call Backström curves. Why Backström? There you see, because Backström in his PhD thesis considered local. In fact, it considered local structure of such curves, or of local rings of such curves. Well, what is it? First of all, what is a non-commutative curve? Commutative curve. Let it be X. It is a pair, consists of X, A. Yeah. X is a curve, usual algebraic curve. A is a sheaf of OX algebras, which is coherent as OX mod. Which means local, it means finitely generated as OX mod. Okay. Then we can consider, as usual, coherent sheaves over this curve, which is just coherent sheaves over A, and so on. Derived category of X, and so on. We can consider usual construction. When it is Backström. What means that it is Backström? It means that for any X, there is a hereditary ring Hx such that Hx contains Ax and their radicals coincide. Just as in this case, in the case above. Then it gives us a resolution. First of all, this is not a. It gives us, in some sense, a normalization. Which is X tilde. It is X and H. Actually, we can. And we have a birational dominant birational map. Yeah. Just as an analog mapalization. But then it is not so good, just as in the commutative case, to consider normalization. It gives very few information, but we can consider then so-called Auslander envelope. Namely, we consider the following thing: X, A tilde, where A tilde is the endomorphism ring of A plus H. Endomorphism is sheaf of endomorphisms. Sheaf of endomorphism, direct sum of A and this normalization. Then, again, we have a recurrent, just as above, of this sort. and which gives us the following things. We can always prove that global dimension of A tilde is 2, derived dimension A tilde we also can put 2, and then it is the same in our case and the derived dimension of X. That dimension to finite derived dimension means that it is resolution, in data resolution. And again, on the level of curves, the kernel of this F, the kernel of recurrent, is the equivalent to the modules over several copies of N. Well, in some sense, it's just sets of vector spaces. So the representations of the modules over A tilde and over A are very much alike. Okay. Moreover, there is another important construction, so-called tilting. Actually, it comes from the same work of Beilinson. I recall this correspondence between P1 and Kronecker. I recall that this correspondence can be constructed as follows. We consider the over P1 the following sheaf. Just two-dimensional vector bundle, which is direct sum of the irregular vector bundle, trivial vector bundle, and twisted by -1. Then it is so-called tilting object, which means the following thing. First, there are no self-extensions. And T, in some sense, generates the category of coherent sheaves. In the categorical sense, I recall that. What does it mean? It means that for any okay, that's right. It is not so important. In the categorical sense, it generates the category. Then, this is general nonsense. A general theory of triangulated categories. It implies that the derived category of P1, of coherent sheaves over P1, is equivalent to the derived category of the algebra and of endomorphism of T, or better often opposite. And this one is just Kronecker algebra. Look, it's very interesting. If we have these sheaves, there are two maps namely if coordinates are xi, then it is multiplication by x, this is multiplication by y. Okay. Now the same can be done. Actually, the same can be done for Backström ring, Backström curve. But it is a bit more complicated. First of all, in a commutative case, and I suppose that our Backström term is rational, which means that the normalization is just a union of projective lines. Yeah, in commutative case, we have this normalization. It's just a union of projective lines. Then there is a tilting of a sheaf, Beilenson tilting sheaf. Just a direct sum of Beilenson tilting for each. Yeah, and we have also the following sheaf, or tilde of a. Oh, no, not that. I'm a bit wrong. This sheaf is just direct sum of a whole singular point of Ox modulo Mx. Let it be Q. Then we must take not a sheaf, but a complex. A complex in the direct category. Direct category of X. Namely, we take T and add Q, but Q shifted on -1. Once shifted. Shifted once. Let it be T plus. Then Burland and I proved that it is tilting in the sense of triangulated categories, which means that there are no homomorphisms from T plus to any of its shifts. And T plus generates the direct category. And again, from general nonsense, it follows then that the derived category in the of X tilde, of A tilde, of this Auslander envelope. Is equivalent to the derived category of the and T opposite. Now you see, we can calculate this thing. We have direct sum. Yeah. One easily see that there are no homomorphisms from right to left. So it is, this thing looks like this. We have here and T, and that's. Here we have nothing. Oh, I tell opposite, so I must transpose. Yeah. And we have nothing here. Here we have and of this extra term, Q, and something here. This is actually is the extensions of Q with T plus. Also. And this is very simple. It's just something like this. Okay, what does it mean? This one we know. Yeah, that is just a union of Kroneckers. This one is just several points. And we have X. So there are some arrows here. Something like this. Plus some relations. Relations are if we have some, say we have here A, B, C, then the relations are C times mu A minus lambda B equals 0, where lambda mu is the coordinate of this singular point, the correspondence of this singular point. So a very simple picture, a very simple picture. Now it is a commutative case. What is a non-commutative case? Is more interesting and more various. Namely, we must take the same. We must take T tilting for H, for this hereditary thing. Take Q, which is just direct sum of AX modulo radical AX of it all singular points. Okay. One moment, please. Якщо я не могу выйти, это класс делаю. I beg your pardon, so I continue. Then we must take, again, T plus Q minus 1. Yeah. And again, we have the same. We have here and T opposite. Here we have and Q. And again, the same. Now, what is it? This is again very simple. Я не могу выйти, я делаю доклад. Okay. So this is again just several points. But this one is more interesting. It consists of so-called ringed canonical algebra. Namely, what is this? A ringed canonical algebra is something like this. It consists of several paths. I will write them in different colors. For the sake of simplicity, some of these paths, I will write some of these paths in this way, okay? Any number. And relations, with the relations. Pi, P1, P2, these are these paths. This path P1, path P2, path P3, path P4, and so on. Pi equals lambda I P1 plus lambda 2, lambda plus mu I P2. Lambda I mu I, again, this is some point of P1. This is, and it can be, we can have not one, but we can have several components. It is one component. Then we add to this picture. Okay, I will erase these relations. We add several points, these points. And then we add some arrows. Say, you see, these arrows also have colors. Corresponding to the colors of the corresponding paths. And plus relations. Which are the following: new arrow times old arrow of the same color. Is 0. For instance, this product is 0, this product is 0, this product is 0, and so on. The product of this arrow with both these arrows is 0, and so on. So this is our tilted algebra. And again, we have that for derived category of X tilde is equivalent to the derived category of this algebra. Okay. Finally, the last topic is the following. We consider this thing. Yeah, in A3. But what if we consider in A2 or in P2 three through a line? It is not Backström. But it is Gorenstein as any planar curve. It means that for any x, if we take OX, it is contained in a OX dash unique minimal over ring such that OX dash mod OX is the ground field. Then what do we have? We have to get with X, we get X dash. Here we have local X or X, here we have X dash, and again, birational dominant map. Yeah. Well, what does it give? And X dash, in our case, is Backström. So we get, it gives us again a resolution. In our case, it consists, it's just the endomorphism of O. X plus O, X dash plus O, X tilde, and tilting in rational case. With almost the same picture, only for singular X. Instead of one point, we get the following: 2 points and 3 arrows, A, B, C, such that AB and AC are 0. Something like this. This is Kronecker part, and this is the new part. So this also called almost Backström curves gives us almost the same picture. Okay, I think I will stop now. Thank you.